Let's take a look at this problem, which is from a textbook. An orange grower finds that if she plants 80 orange trees per acre, each tree will yield 60 bushels of oranges. She estimates that for each additional tree she plants per acre, the yield of each tree will decrease by 2 bushels. How many trees should she plant per acre to maximize the harvest? So this is a case, again, we're going to be maximizing the harvest. And so ultimately, we have to calculate how many trees times how many bushels the trees produce to find the yield. So let's set this up. Let's maybe give a definition here. Let's define X to be the number of additional trees per acre. That's what we're going to call X. Then now we're going to set up our trees per acre. So then the trees per acre will be our original 80. Remember, there's originally 80 orange trees per acre. But then we're going to add some, and we're going to represent that by X. So it's going to be 80 plus X is going to be the trees per acre. Then we want to know the yield per tree. And that's going to be our 60, which we had here, minus 2 times every additional tree, because every additional tree that we add, the harvest is going to be 2 bushels less. So it's going to be 60 minus 2x bushels per tree. So then the total yield per acre is going to simply be the number of trees per acre times the yield per tree. In trees per acre, yield per tree. This, and then let's go ahead and multiply this out so we can work with it. Again, remember how we got this yield. This is number of trees. Again, that'd be trees per acre. And then over here is yield per tree. And then when you multiply this out, you end up getting a yield per acre of, I'm going to kind of I multiply it, I'm going to rearrange it so the squared is first. But you can keep it at the end if you like. So I just ended up moving it to the front. Again, when you FOIL it and add that the coefficients of X, like this. So this is what we want to maximize. We want to maximize this function y over here. So maximize. And of course, whenever you want to maximize a function, when you're doing calculus, you always want to take the derivative and set the derivative equal to 0. So we're going to go ahead and take the derivative of this y here. That's going to be y prime. That's simply going to be negative 4x minus 100. And again, to find the maximum or minimum, we have to set this equal to 0. And then when you work this out, you end up, now notice this will become positive when it goes to the right-hand side, and then we'll have a negative here. We divide by -4, you end up with x equal minus 25. So in this case, since it's negative, this indicates we're supposed to plant 25, or she's supposed to plant 25 less trees per acre. Now, if it would have come out positive, then that would have indicated that she would have had to add additional trees per acre. But since it's negative, she's supposed to plant 25 less trees per acre. Remember, when you see the negative or positive, think of how you've defined X. In this case, we've defined X as the number of additional trees per acre. So if it's positive, we would add additional trees. In this case, it's negative, so we're going to have to, or she's going to have to take away 25 trees per acre. And so let's see what the total, what's the total yield going to be? That's going to be this over here. So finally, what is the total yield? And that, of course, just we can just put this back over here in our equation. Now, of course, the yield per tree is going to go up because we're planting less trees, there's more nutrients for the trees that are there, etc. And so let's calculate this here. And if I put this into my calculator correctly, I got 50 bushels per acre. Now notice that the original case when she started, she was doing 60 bushels per tree and 80 trees per acre. And if you calculate that, with that's 4,800. So the original scenario had 4,800 bushels per acre was the yield. But if she reduces by 25 trees per acre, she'll actually increase her yield significantly per acre. Again, this is assuming like a linear relationship between the number of trees per acre and the bushels of apples she gets. And now, even though in reality it may not be quite linear, this is probably still a very good estimate. If you can kind of estimate how many trees per acre will cause the yield to either increase or decrease, you could maximize the yield using something like this. This problem, we're going to maximize revenue and profits. Actually, this particular problem, we just got to maximize profits. This is similar to the last problem we did for maximizing yield, except we're going to go a step further, maximize profits. And so the question here is, a store can sell 20 bicycles per week at a price of $400 each. The store manager estimates that for each $10 price reduction, he can sell 2 more bikes per week. So if we wanted just revenue, that's all we would need right here. We would just maximize this using this information, but we want to take into account how much the store pays for every bike, because you could bring in as much money as you wanted to, but if you ended up paying more for the bikes than you got in revenue, obviously you would lose money. So here we're going to do this additional thing that the bicycles cost the store $200 each. How much should he charge per bike to maximize the profits? So think about this for a minute. Much like the last problem, we can probably define X to be the number of price reductions, of $10 price reductions. So just let's define X to be the number of $10 price reductions. And so first we're going to have to calculate the revenue. And for that, we're going to need the sales per week. So we're told he sells 20 bikes per week, but it's going to increase based on the number of price reductions. So sales per week is going to be our 20 plus, for every $10 price reduction, he's going to increase this by 2. So that'll be 2x. And then the revenue, the amount he takes in for sale, is going to be our $400 minus every $10 price reduction. So that's going to be 400 minus 10 times x. And of course, if we multiply these together, that'll give us the revenue. So the total revenue and let me maybe just call this R, is going to be, of course, the number of bikes he sells per week times the amount he takes in per bike. And again, if you go ahead and multiply those out and rearrange things, add things together, you end up with negative 20 x squared plus 600x plus 8,000. If you can see that, minus 20x squared, 600 plus 8,000. So again, if you wanted to maximize the revenue, just the amount you took in, you would maximize this. But this time we're going to step further and find out what the maximize the profit. So we're going to have to find out what is going to be the cost. He has to pay $200 per bike. What cost is it going to be per week for the bike? So his costs are going to be $200 per bike times the number of sales he has each week. And when we multiply this out, this is going to be 400x, and once again, I'm kind of rearranging them, plus 4,000. So that's going to be his cost per week, depending on the number of bikes he sells, and that's going to depend on the number of price reductions. So now we want to figure out what is the profit going to be. Of course, the profit will be the revenue minus the cost. And I call it the revenue R minus the cost. And that's the revenue. So substitute everything. And that's going to be minus 20x squared plus 600x plus 8,000. And let's make some room here. I don't want to go to the next line. It'll look a little bit better if we write it right across here. Again, we're going to subtract our cost. This, and again, remember to distribute your negative here when you put these together. And this is going to end up being minus 20x squared. And this is going to be 200. And the 8,000 minus the 4,000 will give us 4,000. This. So this is what we want to maximize. We want to maximize the profit. And so let me call this profit P. Let me just give this a name P here. Be a little bit easier to work with. So we want to maximize this. Once again, if you want to maximize things, we go in calculus, take the derivative. And the derivative of this is going to be minus 40x plus 200. Like this. Again, set this equal to 0. And then solve for x. We bring the 200 to the right, that becomes a negative, divided by negative 40. That ends up being x equals 5. Now, we didn't do this on the last problem. We should check to see if that's a maximum or a minimum. Remember, we do that by taking the second derivative. Let me put this I'm gonna sort of squeeze it in over here. So the second derivative, and we would normally take the second derivative and substitute this. And of course, no matter which you substitute here, this is going to be negative. So that indicates this value we got here is a maximum, because remember, if the second derivative is negative, that indicates that our critical point is a maximum. So this is a max. And so the question is then, what price should he set the bikes at? And we price the bike is what we call our revenue per sale. That's going to be our 400 minus 10 times 5, because there's going to be 5 $10 price reductions. So that means he should set the price at $350 per bike. And then if you wanted to find the actual profit, you could plug the 5 back into this equation here. That's going to be minus 2, it can be minus 20. That's 5 squared. $205. Over a little bit. Well, 4,000. And if you put that into your calculator, this comes out when you put in your calculator. I got $4,500. Like any of these maximum or minimum type problems, you set up your equation, take the first derivative, set it equal to 0. Sometimes you have to test to see that it's a maximum or a minimum. And then, so in this case, we determined we would maximize the profits, because that's what we're trying to maximize, by having 5 $10 price reductions, which means the bike should sell $350, resulting in a profit of $4,500 per week.